completed our discussion on interpolation as well as numerical differentiation. Now, before we close this week, let us see an example combining both interpolation and numerical differentiation. Let us assume a one-dimensional solid slab that is in x dimension, where we are measuring temperature at 3 different locations. Here I have x equals 0, then x equals 10 and x equals 20. And in these 3 different locations, the temperatures are given by 300, 350 and 450 respectively. We are interested to find temperature profile, which means T as a function of x. We understand that what we are asking here is an interpolation. So let us go through the interpolation and let us use the Lagrange's polynomial. So then Tx is equal to Lix fxi, and I goes from 0 to 2. There are 3 points. So 0, 1, 2. That means L0x fx0, L1x fx1, L2x fx2. And we know that Lagrange's polynomial, this Lix, is product of j equals 0 to 2, j not equals I, x minus xj, xi minus xj, which gives us these 3 polynomials L0, L1 and L2 like this. L0 is x minus x1, x minus x2 divided by x0 minus x1, x0 minus x2. Similarly, L1 is x minus x0, x minus x2, x1 minus x0, x1 minus x2, etc. So is the L2. So now we will figure it out what would be the L0, L1 and L2. So for L0, I take this x minus x1, x1 is 10, and x minus x2, x2 is 20, divided by x0, x0 is 0, so 0 minus 10 divided by 0 minus 20. I can simplify it, it comes to 1 by 200, x minus 10 into x minus 20. Similarly, L1x, I have x minus x0, x0 is 0, x minus x2, x2 is 20, divided by x1 minus x0, x1 is 10, and x1 minus x2, x1 is 10, so 10 minus 20. Simplifying, it turns out to be minus x by 100 multiplied by x minus 20. Now L2, in same way, I can write x minus x0, that is 0, x minus x1, that is 10, and x2 is 20, so 20 minus 0, 20 minus 10, it gives us x by 200 multiplied by x minus 10. So therefore, my temperature profile Tx is equal to sum I equals 0 to 2 Lix fxi, and that gives me this fxi is 300, 350 and 450, so 300 L0x, 350 L1x and 450 L2x. I can now write this expression for L0, L1 and L2 here. Plugging in, I have this expression for Tx, 300 by 200 x minus 10 to x minus 20, etc. Now I can simplify and I get this expression of Tx here, 1 by 4 x square plus 10x plus 1200. You can check it out. If I plug in x equals 0, this to 0, 1200 by 4, 300. So it seems all right. You can check with 10 and 20 as well. Okay then. If I go for a different time, let us say this is a transient problem, this is not a steady state problem. So in a different time, my temperature changes and now my temperature is 320, 390 and 510. Now do we have to do the calculation all over again if I want to find the temperature profile Tx here? Actually no, because This L's are function of x only. So my location x, as long as they remain same, the change in temperature doesn't require new calculation of L. Whatever the L0, L1 and L2 we have calculated, we have used only x, and we'll keep that here also. So my Tx will be this Lix Fxi, and the temperature has changed, so I have 320, 390, 510, but this L0, L1 and L2, they are same as before. Now we move ahead. We know that in Fourier's law of heat conduction, the heat flow per unit area in this one-dimensional slab will be given by, this is heat flow per unit area minus K into dt dx. So K is the thermal conductivity. So thermal conductivity, if this is 100 watt per meter Kelvin, find the value of Q at x equals 0, means at the end. So let's say this is my temperature profile. I want to find the dt dx first, and my dt dx, once again you see that it only involves the derivative of L0, L1 and L2. It doesn't matter what is the value of T0, T1 and T2. Once I have this L0, L1, L2, I am fine. Derivative will not change when temperature changes. So this is my L0 x, 1 by 200 x minus 10 multiplied by x minus 20. If I take the derivative, it will come as 1 by 200 x minus 10 plus x minus 20, which equal to 1 by 100 x minus 15. Similarly, I take L1x, that is minus x by 100 into x minus 20, and its derivative gives us minus 1 by 50 x minus 10, because x square minus 20x will be twice x minus 20, then 2 cancels here, 100 becomes 50. Similarly, L2 prime x will be 1 by 100 multiplied by x minus 5. Overall, I am now ready to find this dt dx, and my dt dx will be minus 15 by 100 T0 plus 10 by 50 T1 minus 5 by 100 2. So I only think that what I did is that I put 0 in place of x. I didn't put any value of T0, T1, T2. It's only x equals 0 I have put, so it becomes minus 15. Here I have 10 and here I have minus 5, which gives us this expression minus 3 T0 plus 4 T1 minus T2 by 20. It should look familiar to you from finite difference calculation of 3-point derivative. Here the grid size is 10, so 2 delta x is coming here 20, and this is 3 T0, 4 T1, T2 is coming as one finite difference. So my temperature gradient is this minus 3 T0 plus 4 T1 minus T2 divided by 20. This is in K per centimeter. I have here the value of conductivity is watt per meter, so you have to be careful in checking the units. We cannot mess with meter and centimeter. So our Q at x equals 0 will be given by minus k dt dx x equals 0, and that will be this 3 T0 minus 4 T1 plus T2 by 20 watt per centimeter square, not meter square. If you go back and see our discussion on higher order differentiation, where we have found similar kind of derivative using finite difference, if you check that out, you will find that coming from the polynomial side and coming from the finite difference side, they give same expression. You can ask yourself that why are they giving same expression even though there are different methods. Both the techniques are powerful for numerical differentiation, and in practice we use both of them whenever what is necessary. For your exercise, you repeat this problem using finite difference. Do not use polynomial interpolation here, just use finite difference to find the derivative of temperature. Verify the result, it should match, and you argue that why it should match with the polynomial interpolation. You post your comment in the forum that why it will match, and we'll discuss it later. So thank you. That's all for this lecture. I'll see you in next class.